welcome back. So, welcome back. I want to spend 2 more minutes on this because I like it as a topic. It's a good reason to talk about it. So, remember before the break that I talked about Turing's mathematical contribution, in which he showed basically that, or he gave a mathematical foundation to the question what can be calculated and what cannot be calculated. Yeah? And the question of whether if we have some logical formulae where we know what we want to be entailed and what we do not want to be entailed, the question is, can we find an algorithm that always gives an answer, the correct answer to this question? Turing went further. He came up with a mathematical framework for allowing us to say whether things are computable or not. And basically what he did was incredibly clever. That was before we even thought about making these machines, before we implemented the first of these computers, he thought about a mathematical representation of what is it, how can we do computing? And these were his so-called Turing machines. And the Turing machine, I tried to look it up in the break, but I failed, so I might have the details wrong here. But the idea was that you have a tape where you can write some letters out of a finite alphabet, and the only thing you can do is write, move to the left and move to the right. There are, I think, and read, yeah. So read the letter that's in there and write something to the board and move left or right. That looks like a physical machine here, but he formulated that in a mathematical function. But he called it a machine, and it is a machine. It is a Turing machine, and he then showed that this mathematical machine is so powerful that you can solve any problem with this. You can compute everything that can be computed in general. So every algorithm we write nowadays can also be implemented with this. I do not recommend you to try to implement your next project on a Turing machine, because it's not meant for it, but it's meant to show that everything we can do can be also done on this machine. And then the trick to show this notion of undecidability, or that there are problems that cannot be solved, that cannot be computed, is that he worked on this very, very nice, relatively simple, beautiful mathematical model to show that I can do something with this machine where the machine cannot give me a right answer. Yeah? And that is the so-called halting problem, which is sort of formulated here. So the first thing he showed in, I think, his PhD thesis was that the Turing machine can calculate everything that can be calculated. And then basically he comes up with a problem that you give as input to his Turing machine, which the Turing machine cannot solve, which basically proves that there are problems we cannot solve. Problems we will never find algorithms for doing this properly, for giving us the proper answer. And the problem he comes up with is that if I have a machine which can determine whether it holds in finite time or not, and I think you need to input it negated, so to determine that it doesn't stop, and you take it as input to itself, then the machine should be able to tell itself whether it stops or not. And if it stops, it should not stop, and if it doesn't stop, it should stop. And it comes up with this kind of contradiction in itself by construction. And if you do more formal logic, you will follow up this. It's one of the most beautiful results in mathematical logic, in computational logic, where you basically show, based on a very, very simple mathematical model, you show that there are things in life that we cannot solve automatically with automatic computation. So what has it to do with our first order, our logics? Basically, this has to do with the property that first order logic is undecidable. is one of the examples of those languages for which we will never be able to find an algorithm that tells us for all the formulae that we have whether it's entailed or not. It has a nice property to sort of rescue the whole language that is called semi-decidable. And this semi-decidability means that if the formula is entailed, I can prove it. But if it is not entailed, I cannot prove it. And if I have an algorithm that shows that something is entailed, something follows logically, it will eventually find the solution. It will find the formula that it is entailed. But if it continues running on, I cannot say, okay, I'm stopping now, and it's not entailed, because it could be the next one that could be in the next instance, I could find that it is entailed. So there is never a moment where I can say, I've now searched sufficiently for my solution, for the question, for the answer whether it's entailed or not. The algorithm would run forever if it's not entailed, but I have never any moment where I can say I can stop now. And that's the notion of semi-decidability. Yeah? So this is a sort of a negative property of this first order logic that goes back to results from Turing and were then extended later in the second half of the 20th century. That first order logic is very powerful in representing the things as we've seen now, very elegant, but we will never be able to show that something is not entailed. Okay, so on the one hand, we have this first order logic as an elegant modeling language. And then we have propositional logic as an efficient reasoning language, as I will show you tomorrow. And I will explain how you do this efficient reasoning, so automatic reasoning is a proper part of AI tomorrow. You have to believe me right now. So the trick is now to say we translate our first order formula into propositional logic, which is called propositionalizing. And I've already given you some hints on how to do that and why this is possible in our specific problem. And that obviously has to do with the fact that we have a finite domain with relatively small number of objects that we can have in our models, so we can restrict our representations relatively strongly in terms of size. And then we can use the notion of entailment to make our decisions on the strategies that we want to play in Schnapsen. And we can do that on the basis of a reasoner that gives us entailment in propositional logic as a result of the translation process. And we're going to do that tomorrow, looking at Davis-Putnam decision procedure, which is an algorithm that decides entailment in propositional logic. And I will show you how it works and why it works. There is an important property that you need your formula in before you can apply the Davis-Putnam procedure, and that's that they need to be in some kind of normal form. And I spare you the normal form today, but basically the idea is that you have you can transform any formula in propositional logic in a formula which consists of one big conjunction, so of several disjunction of atoms or negated atoms. So I have then a formula which would be, so this must be or, not B or C. And this is one big conjunct of, and write it like that, this. And this is a specific representation that you can have as input to your Davis-Putnam proof procedure. And I just mention it now because it's good if we can already write down our formula in this format and if we take care of this a little bit. And this is also why you won't see many disjunctions, conjunctions in the representation that I'm going to show you in a minute. Okay, so we have to make sure our formulae after propositionalization are in this closed normal form. And then what the method that is used is a proof by refutation, because this Davis-Putnam procedure determines whether a knowledge base is satisfiable, whether there is a model. And there is a relation between this notion of satisfiability and the notion of entailment, namely by showing that if you add the negator fact to your knowledge base and you check the satisfiability, and this is the result is it's unsatisfiable, then you have proven entailment. So let me write that down properly so that so if I have a knowledge base and I want to check whether a formula follows, so this entailment, this is logically the same as if and only if I add the negation of the formula itself, if this is unsatisfiable. Yeah? Which means that I cannot find a model for this. And this is logic. It is in principle very easy to see. So if this always is true, suppose that it's false, when I add it to my knowledge base, then there must be a contradiction. Yeah? So that's the basis of having these proofs by refutation. So what we need to do is we need to specify the information of our knowledge base in closed normal form, and then the thing we want to prove, so the strategy that we want to apply, we add in a negative form, or the checks that we want to do for the strategy, we have to add in a negative form to the knowledge base. That was what we did here. So now let's look into how to represent these things in first order logic and then translate them. So what we have to do first is we have to come up with the strategy. So what is the strategy in Schnapsen? That will be the task for this milestone. What would be a strategy to play if we get a deck of hands, like we did yesterday with the rather complicated strategies, I have to say, yesterday, with whether to not to play a king because you could spare it for the next move because you might get a marriage. So these kind of things. We have far more simple strategies here because the translation is already rather tedious. And but this is the kind of thing we start with. And then we write down the strategy in first order logic. We translate it in propositional logic after we've given all the background knowledge, all the structural knowledge about the games, and then we translate the knowledge base into propositional logic closed normal form. We add the negation of what we want to check, whether things are entailed, and then we check entailment or unsatisfiability in this case with a reasoner. So that's the shopping list. And then you can think of many different logical strategies now translated to our Schnapsen example. So the first one would be, if you have a jack, you always play a jack. It's a very simple strategy. I think in the first phase, of course, we are now only dealing about the first phase, because if you manage to get to the second phase, you can simply play your min-max algorithm, play it completely, and you know whether you win or lose. So you don't need this knowledge-based strategies for the second half, because we have a complete optimal strategy with min-max. But here, a strategy could be always play the jack. Similar one would be always play the cheapest card. So if you don't have a jack, play the queen. If you don't have a jack and a queen, play the king. In the first phase, this is a strategy that makes sense in a way, because you want to lose as few points as possible to your opponent, and your opponent can win in principle. In most of the games, can win all the cards he wants or she wants. Another strategy could be play the wedding first. If you have a wedding on your hand, play it. Play the highest cheap card, play the highest card, save a wedding up for later. That was one of the examples we used yesterday in the lecture. Or play down from the top. So if you have all the top cards, you can just play out and hope for the best. Yeah. So these are different strategies. I'm not sure which of them really works best. That would be, for example, already an example for a practical assignment for the final project. Although I have to say that implementing these strategies and formalizing them in the logics, translating them to propositional logic could be quite a lot of work. So I'm afraid that this might be unrealistic to do many of them. And I also want to sort of give an advanced warning that this is a principled approach that I think gives very interesting insights into usage of this explicit knowledge in making choices in these games. But the way we are doing it now in this course is probably not one which you want to apply in practice. Yeah, because this first order logic, second order logic translation, it's a relatively, or at least you want to automate it. So we have to discuss that later. So how would that work for a strategy that I call the play the jack? The first one of the list is your algorithm. The algorithm, how it works in the implementation of the knowledge-based bot is that it checks for does a card adhere to one of these strategies. So you just loop through all the 5 cards you have on your hand. You check whether this card, the first one in your loop, adheres to one of the strategies, and if it does, you play it. So basically here, what the only thing you have to do is whether, if you go through the list of all the 5 cards, your loop of the 5 cards, you check whether it's a jack, and if it is a jack, you play it, and if it's not a jack, you don't play it. Yeah? So it's an extremely simple strategy, and it's simple defined. So the strategy is, if something is a jack, then you play it. So play jack is simply the information that if it's a jack, we play it. So that is in first order logic for all x. So for any card, the command, the rule of play the card is given whenever this card itself is a jack. So now if you translate that to propositional logic, you see here the intermediate representation. Then it basically means that if the first card is a jack, so this is meant to stand for a first card is a jack, and this is meant for play jack 1. And this is another way of representing the implication in propositional logic. It basically says that either you're not playing the jack or your card is a jack. So if you're not playing the card, and basically you have to do that for all the cards in the game, so 20 times. And you have, this is the representation of the one direction. So if you have a play jack, then it must be a jack. And this is the other direction. If it's not a jack, if it's a jack, then it must be the strategy. You must apply the strategy. So it's both directions represented in propositional logic, and you have to do that for 20 cards. So something you want to write a quick script for that just writes this statement 20 times in order to translate this statement into propositional logic formula. And then the only thing that's missing then is information about which of the cards is a jack and which one isn't. And obviously we have the state representation of the game state that we can translate this into, so we know that the card 4, 9, 14, and 19 is a jack. And then if we get card number 4, then we know this property holds. So then this property also means that the jack is played. So all this representation does is basically, this is my rule, is should I apply the play jack strategy on the card X? And I should do that if something is a jack, because by definition this is the all we need for the strategy. And then we can run a reasoner, and the reasoner tells us, oh yes, play the jack if it's card number 4, don't play the jack if it's card number 24. 24 doesn't exist, 17. Yeah. Okay, and in the code, what I've written down here as the knowledge base, you just have to add as a clause what I said here, that jack 4 is true, and jack 9 is true, and jack 14 is true, and jack 19 is true, and that would be then part of your clause set as your input to the prover that is provided in the code. Yeah. So these four things are is this information down here. So that's the information about the game and how it is implemented in the engine. And there's maybe more information we need, namely the game information of what cards are in there and what cards are out there. But that's not here yet. This is the other information, these things here. So each of them, as you might recognize, are exactly in this form. So it's a conjunction. Here I use the other symbol for conjunction as I want you. I would. So here conjunction of disjunctions, and this is the way how you add this to your knowledge base, just as a command, conjunctions individually per, and then you have the two disjuncts here, parts of the disjunction that you would add. Yeah. So this is just the technical way of adding this information to the code on the in the Git for the KB engine that we provided. Yeah. And as you can see, we need already quite some of those. We need 2 for each direction of the implication. We have to do that for 20 variables. It's not a very efficient way. You can probably do this in a more efficient way if you think a bit about it. But this is a systematic way of doing it. And then the question is, and that's why we needed this proof by refutation idea, then the question is, should I play the card 14? So I go through my list, through my loop, and I get the card 14. I have to translate this into a question. Should I play the card 14? Does it adhere to the play the deck strategy? So I add it to my SAT solver in a negated form, and the SAT solver then runs a satisfiability check. And in this simple case, it should say this is unsatisfiable because I know that P14 is a jack. I think it was. Yeah, P14 is a jack. So basically, adding not PJ14 will give a contradiction. And that basically means that PJ14 is entailed. So that playing the card number 14 will be according to the play jack strategy. Yeah, so that is the pipeline that you have to follow. And now the question is then, how do you implement those strategies in this logic? So for example, playing cheap means that it's off a jack or a queen or a king. Yeah. So it doesn't make it's not yet an implementation of play the cheapest. Then you would say if it's not if none of the 5 cards you have on hand is a jack, then the queen is the lowest, and so forth. So this is simply, we take one of the 3 cheap cards and we check whether the card I want to play is one of the 3 cheap cards, either a jack or a queen or a king. And it's just one line of code here, how this strategy works. And I do exactly the same. Again, we have to now also sort of type all of the cards from 0 to 20, 1 to 20. And then basically this is all we need to represent. Again, we translate this, or we write this down in propositional logic, and we add the negated information of, is this specific card in my hand, is it the card to play according to the play cheap strategy? And it will return yes if it is a queen, a king, or a jack, and no otherwise. Yeah, that's the idea behind these knowledge-based agents. Here's one last one, a bit more interesting one, and that is if you have a trump wedding, you want to play it. Yeah. So how do we represent that? A trump wedding, what is a trump wedding? So I want to play the queen of the trump wedding, so I want the X to be a queen, I want it to be trump, and I want something to exist of the same color, which is a king, and which is on my hand. So you have to represent what is on my hand, you have to represent what is a king, you have to represent the question of same color, which basically means you have to represent the question of what is the color of the card in the first place. And all of these things need to be made explicit in our knowledge base. So as I said before, this can be quite tedious. So the definition of same color is easy in first order logic. We just say X and Y have the same color if they are both predicate color, cloud, or color diamond, or color heart, and so forth. So that's an easy one. But first we need then to say which is the color of the cards. So I believe in the code there is already a distinction between the sort of game information, the static information, and the new information. And basically the point is that all this information, namely the card value of the cards and the color of the cards, they never change during the game. So that is assigned by the game engine. So this is something you can put into your into an extra file that you just upload, and that's information you always have, you don't even look into. And then you can concentrate on writing your strategy in your favorite logic of in first order logic. And then we need information about the state I'm in, the cards I have in hand. You can also model what cards does your opponent have, what is the known card, and so forth. This is all something you can explicitly model. The big problem is that if you look at this statement here, first of all, we need to, if we propositionalize, we need to do this for every x in the domain. So we have already 20 axioms to do this. But then we also need to do this for all possible existential things that are other cards that my value x could be related to. And that basically means that there is a big blow up of possible statements in propositional logic. And yeah, so the big question in general is, does this work in general? And obviously the answer that you could all probably give me is that it cannot work in general. Why can it work in general? Think of Turing and his arguments. So what would happen if we could propositionalize every first order logic formula? And I might not have said that explicitly, but propositional logic is actually decidable. So you can write an algorithm that tells you exactly whether it's entailed or not. Yeah?
Then to the first order logic being unsatisfiable, and therefore you could prove that it was entailed, and therefore no one could.
Yeah. So if you could always translate a first order formula into a propositional logic formula and decide the propositional logic formula, you would have found a decision procedure for first order logic. And we've just shown, or I've hinted at it, that it was proven that first order logic is not decidable. So it cannot be the case that we always translate it into propositional logic, because otherwise we would have sort of shown that something worked that was shown not to work. Yeah? Let's first look at the mechanism more systematically. The idea is that whenever you have a formula for all V of A, then you can simply replace all the ground atoms of your domain and rewrite the formula. Just as we did here, we have now a finite set of ground terms G, and this is the example from King John and Richard again, and we just have to fill in all the substitutions, and they are all valid formula that follow from it. And if you do this for all the possible objects, you also have a complete method for translating this. So John, you have to replace X with John. You have to replace X with Richard to get this formula. But then you also have to apply it for all the functions. So we have a function father of John, and we have the function father of John, and you have to do it again for father of Richard to get the complete set. So that's in a way is how the algorithm works. So it's just this substitution, and you do it for all the ground terms. And in our example, And in our example, we do not have any function symbols. That's one restriction in first order logic, which makes this possible. And we have a finite set of objects in the domain. That makes a difference. So that's why this works for translating our formula into propositional logic. But this doesn't hold in general. Let's go to the other one. That's the existential quantification, where you also need to do a substitution. So for any sentence you have in your language and the variable v, you add, in principle, in the reasoning algorithm, you add a constant that isn't already in your domain. That's called scholemization. It's a process. And in our case, the situation is easier because we have a finite domain, so we can pick one of the objects we have. But in principle, you create a new constant here if you do this algorithm. And wait a second, I get to that. So if we go back to the example that we just had seen, we have a universal quantified formula. We just show if we have this one axiom and we have these statements that sort of do the grounding, then we can do it completely in all possible ways. There is no existential quantification, and we can now propositionalize the new knowledge base by simply filling in all the grounded terms, so the constants and the functions applied to constants, to get from a first order logic knowledge base to a propositional logic knowledge base. And even though this is written as King John, as if this was still a first order function or a predicate, this is also simply a propositional variable, as there is nothing we can do with these things anymore because there are no variables anymore. So basically all you do here is you replace all the variables by all possible values of objects that you can find in your knowledge base according to the finite things you have. And only if you have an existential quantification combined with this, or you have an infinite domain, you get into trouble. Yeah? So you can translate every formula, you can propositionalize, but the problem is that you cannot make sure that this propositionalization is finite. So there is where this undecidability result sort of moves to our problem. There's a general result for our specific problem. I don't think we face this problem. And I'm doubting a little bit at the moment because I said that this can happen because of the existential quantification. Therefore, you would maybe have to develop infinitely many new objects. But I think this only happens when you have function symbols and predicates, multiple predicates. So I think in our case we are safe, and there will always be a simple way of doing this. But I have to come back to that tomorrow. So here this is mentioned as the problem. If you have a function, then you can always apply the function to the result of applying the function. And that's why you would get these infinitely many functional symbols, and that's why it's good that we, in our case, we don't have any functions applied to objects. That makes it, that's the answer to what I just said. This gives us the guarantee that we always will only have finitely many of those rounded terms to which we can apply this. And these are then three results that are the results that are important from a theoretical perspective. The Herbrand was the person who really looked at those finite and infinite groundings of the sentences. So how can we write propositional statements from first order statements? And he basically said that if it is entailed, then there is a finite subset of the propositional knowledge base. So that's the good result. If we are entailed, then we can use this method to actually find the answer. Yes, it is entailed, but we are still sitting with the problem, what happens if it's not entailed? And basically the fact is, as I just mentioned, that you can have infinitely many of those functions, of those terms, by applying functions to functions, and then basically you do not have the finite property anymore. So this is the important result. I can propositionalize a first-order logic formula in a finite propositional knowledge base, and then I can use the decidability of propositional logic to decide my first-order formula. But this only works if the formula is entailed. And if it's not entailed, it doesn't mean it doesn't mean the opposite, so that I can use this as a proof for entailment and non-entailment in first-order logic. And that's basically consistent with the results from Turing, that there exists an algorithm to say yes to every entailed sentence, but there is no, and there cannot be an algorithm to say no if the thing is not entailed. Yeah? So the answer to this, there exists an algorithm that says yes to every entailed sentence. That is the result that we have up here. And the other one comes from Turing's result of the halting problem. And it basically is due to this infinite loop that you can build in your decision procedure. Okay, so that was a sort of stepping out again to the theoretical properties of this of these decision procedures in the different formalization languages. We have a way of translating our first-order formula into propositional formula, and then we can apply a propositional reasoner that I'm going to talk about tomorrow. And then basically the task is now, do these human strategies somehow work if we compare them with strategies that are, for example, learned, or simple random guessing strategies, and so forth. And there are a number of those that we can implement in the practical assignment that I would really like to see implemented. And so please try them out the next days. And let's see how this works. So now, I spoke to one of you, and I don't know where you are anyway. So he had already implemented some of these strategies, hard-coded into the algorithm. So always play the ace if you have one. So you just run through your code, and if your card is an ace, because we have this information, of course, then you just play the ace. All of these strategies that we've talked about, you can hard code into your own code. So basically, if you look at the Pullybot, I believe that it takes always the highest card you have. Depending on the question whether that's a good strategy, the problem here, or the point to make here, is that would be also a strategy that you could implement with the methods that I've just talked about for 30 minutes. The question is, so, isn't this done already? Or what is the difference of doing this in this sort of complicated, knowledge-intensive way where you write things down in a first-order formula, or whether you write the same thing down in your code directly? And I think that's a very important question. If you have one strategy that you want to write down, it will probably be more efficient to write it down hard-coded in your Python program. Because everything you do here, you can also do in your Python program. But if you want to compare strategies, and if you want to talk about strategies, and if you want to make your strategies explicit, then representing it in those logical languages, particularly if you have some more sophisticated kind of reasoning over possible states and situations, then representing things in this generic logical formalisms and using the generic tools for this doesn't make sense. So I'm not advocating that whenever you have some strategy that you want to do, that you need to implement this in a logic-based approach. Absolutely not. So these logic-based approaches, they are very often overkill, because they are pretty heavy generic reasoning algorithms. in this course I want you to do this, and it might feel a bit heavy what you do, but the point really is that this is explicit knowledge that we can reason over. We can compare strategies explicitly. I could say, for example, that you come up with a specific strategy, and I also, and we check whether a strategy follows from another. So if you play the Jack strategy, for example, you always also play the Jeep strategy. So we can compare explicitly the different strategies. And that's an added value that you need if you explain things to people in intelligent systems. So if you have, we are now talking about games, and not many people care really about what the strategy, so everything is fine. But if you now translate this into strategies for treating people who have cancer, then I think it's rather important that you understand what this strategy is, and that you can reason over these strategies, and that you can compare the strategies. So making those strategies explicit is here the goal in itself for this specific project. Yeah? So that's a crucial difference, making the things explicit and declaratively written down so that we can talk about them, and then doing all the reasoning over, we have that done by the machine. So the final project is really about comparing the different strategies on the one hand, but not even more important, the different ways of building intelligent systems. So in the course, we are now, I think you have now seen 3 or 4 different ways, really conceptually different ways of building intelligent systems for this specific simple problem. And you will not get an answer from me which one is the best one, because I think it depends on the situation you're in. So it depends on the implementation you have. So it's a really interesting question of what is the best one. It might be that a strategy that works after the first trick doesn't work after the second, and so forth. And all of these give us interesting research questions, such as what is the impact of the sampling rate for the perfect information Monte Carlo bot? So if you sample only 8 runs, that should be different if you sample 200 runs, or if you sample from the top to the root, or if you sample from the top to the second phase, and you then do an alpha beta pruned min-max algorithm. That should give you different results. And the question is really, for us as an AI researcher, which is the best strategy to apply? Other questions are, can a knowledge-intensive bot beat a learning bot? And why? Which is the best strategy in the knowledge bot that works against the learned bot? Or even if you use a knowledge-based bot as a training bot for a learning bot to play against, will it learn the same strategy? And these kind of things. And then there are even properties like, what are the computation properties, the runtime of my algorithm? Does it take 3 days before the next move comes back? It's not a very exciting game if you have to wait for 3 days. These kind of things is everything we really want to understand better about the algorithms that underlie these intelligent systems. And what you have to do, and I talk about this next week again, is write a standard research paper as you would submit it to a scientific conference with all the bells and whistles, and also in the required formats that we would use to submit to a proper conference. And before we can do that, of course, you need to implement as many different kinds of intelligent bots. Do not take the Git, the code that we give you as a limitation, but go wild, implement what you want to build. It's just an offer to make you start nicely, but you can, of course, implement it no matter where you want it to implement, and just go ahead. And then you use the infrastructure, play tournaments against your own bots, the bots that we provide, and so forth, in order to come up with interesting research questions. And more on that tomorrow. Thank you.
Would something like around like rollout strategies for reinforcement learning